Hello to all tuning into the Aerospace Ambition Podcast. I'm Marius, here with Kieran, my fellow co-host. As aerospace engineers, we are at the intersection of sustainable aviation and artificial intelligence. In today's episode, we are focusing on the critical issue of contrail prevention and management. Let's find out who we have the pleasure of speaking with today. Kieran.
So today we're joined by Professor Stephen Barrett. He's the HN Slater Professor of Aeronautics and Astronautics at the Massachusetts Institute of Technology, or MIT, where he is head of the Aeronautics and Astronautics Department and director of the MIT Laboratory for Aviation and the Environment. His research focuses on helping the aviation industry achieve zero environmental impacts, with focus areas including low emissions propulsion, contrail avoidance, and evaluating the sustainability of biofuels. Stephen, thanks for joining us on the show.
Thanks so much. It's great to join you.
Yeah, so as we've spoken about in previous episodes, there's, of course, a multitude of different environmental impacts caused by aircraft emissions, namely CO2, but also the non-CO2 effects, including contrails, NOx, and aerosols. And in talks you've given in the past, you've presented these effects in terms of their economic impacts. So not just climate effects, but also the local air quality effects and what they, the impact they have in terms of dollars per ton of fuel. So could you please elaborate on these different effects from this context?
Yeah, so at a high level, there are many impacts of emissions. And those include air pollution, and that's the effect on human health, but also climate change, which you could view in many ways, such as average temperature increase, or changes in sea level, or even changes in crop productivity or disease vectors. So it's very complicated to compare all these different kinds of environmental impacts of emissions. So in some contexts, it can be useful to come up with a single metric that enables you to compare different emissions and the total environmental damage caused by those emissions. And the reason is that way you can sort of prioritize where to put investments, where you can see you can get the quickest benefit from a different investment. So having a single number helps you to do that prioritization.
So what's the highest in terms of cost down to the lowest?
So there's a bit of uncertainty in the exact rank order. So I can give you sort of the leading contenders and then the lower one. So the sort of first order impacts come from NOx, CO2, and contrails, and they have different impacts. So in the case of CO2, everyone will be familiar that that's primarily of concern for climate in that it increases global temperatures. And those numbers in those talks you referred to come from the literature of environmental economics, which associates increases in global temperature with economic damage. And there's a well-established sort of scientific basis for coming up with those estimates, but those estimates are still have uncertainty associated with them. Secondly, what's really unique about aviation is that the emissions are at high altitude, and so when you emit water vapor at high altitude, it often can be cold and wet in the atmosphere, and that water can freeze into an ice cloud, basically a contrail, condensation trail. And those are thought to cause about as much warming as all of the CO2 from aviation. So that's kind of the other big climate effect is contrails. And then the third biggest impact environmentally is the NOx emissions from aviation. So that's oxides of nitrogen. And that comes about because we burn fuel in the atmosphere that is 78% nitrogen. And so just because you're burning the fuel in the Earth's atmosphere with a lot of nitrogen, some of that nitrogen gets converted into NOx, which is NO and NO2, and that's harmful to human health both directly and indirectly. So those are the three big things: CO2, NOx, and contrails.
What I saw at the presentations you gave and also on the conferences in general was that a lot of the focus recently has been given the topic of contrails and the negative effects of contrails. Do you think it takes away some of the important focus to be put on public health as well? Like, is it a discussion that is balanced enough right now?
I think it's a great question and a difficult one to answer. So to give some historical context, when I started out in the sustainability field for aviation, a lot of focus was on NO2. So that's a subset of NOx. and that was really focused on public health impacts. And that sort of media frenzy around that topic helped to raise the visibility of public health and air pollution. And the world sort of then moved on to increasingly understanding the importance of CO2 and mitigating CO2. And now we're sort of beginning to understand, in terms of the public discourse, the importance of contrails and mitigating contrails. So I think at some level, it's inevitable in terms of how public discourse moves that there'll be a focus that changes over time. So in that sense, it's good. But I think as the focus moves, it's always important to try and not forget the previous areas of progress we've made. So, for example, air pollution still matters. It hasn't been solved. There's still a lot to do, especially in some areas like aviation, where it's hard to have emissions control like you can with cars and lorries. And similarly, CO2, everyone understands that still really matters. So I think you do have to have a spotlight for a period on a new topic while trying to sustain the interest and understanding of the older areas.
Yeah, so one thing is the discourse and the attention that we spend living in an attention economy, right? But then we are engineers, so we try to quantify it. And for that, we have metrics. But picking the right metric is not that obvious. So they all come with benefits and drawbacks. Within the recent European Commission Innovation Fund call, for the first time, I believe, it was stated that contrails are a problem, and we are calling for solutions to mitigate the negative effects with that. And the European Commission, or within those papers, they used the GWP 100, so the global warming potential for 100 years, to quantify that problem. How do you feel, or how do you see this choice of a metric, and which metrics are maybe in a better position or worse position for maybe also regulation?
Yeah, I mean, metrics are an important topic, especially when it comes to regulation. I think there's a sort of slightly different perspective when you're talking about the public discourse, which sort of eventually leads to political pressure to create, for example, this call you referred to, which ultimately came from increasing awareness of the public and politicians and so on. And when you view it in that way, I mean, there are many metrics, and any scientist you stop on the street will have their own favorite pet metric, and they'll all have various pros and cons, and we could have ferocious debates about the merits and demerits of metric A versus metric B. But I think what matters more is just that the metric has some way of accounting for time horizons. So, for example, if you take contrails, they are really, really quite strongly warming, but over a very short time period, whereas CO2 has relatively weak warming, but over a long time period. So if you chose a metric that was sort of, in a sense, instantaneous, then you would weight things totally towards contrails. Whereas if you only cared about the very, very, very long term, then you'd weight things totally towards CO2. So the key thing is that you somehow account for both of those in a way that's rational and sort of tied to, the human experience of lifespans or something like that. So provided those criteria are met, then there's many different metrics you can have that will give slightly different answers. But essentially, all of them tell you that CO2 matters and contrails matter. And maybe it's 1/3 CO2 and 2/3 contrails, or maybe it's the other way around. But either way, it doesn't really change the kinds of decisions you'd make. You still want to tackle both of them. So as long as the metrics are in that kind of realm, I think it's fine.
Okay, so different metrics have different results, but I think that most of the metrics right now indicate contrails are somewhat of a problem, and hence there is a public debate on what can we do right now. So our previous guest, Joachim Mayholm, he is basically raising the awareness about contrail management, and we have this tradition in the podcast that we pass on one question from previous guest to the next one. So he asked a question that's addressed to you, Stephen, and that is, what do you think are the 3 biggest problems holding back the adoption of contrail management at scale?
That's a big question. So I think question or number one is that we have a strong understanding of the overall impact of contrails on climate that has been developed over some 30 years. And that understanding, while it's strong in the sense of lots of research and it's been well characterized and heavily reviewed, there is uncertainty in that estimate. And that uncertainty is quite significant. It's a factor of a few, higher or lower than the central estimate. So I think the challenge there is that people misunderstand how to deal with uncertainty, which is that you don't deal with uncertainty always by waiting for it to be reduced. Sometimes you have to make decisions despite the fact that's uncertainty. And I think this is a very strong case of that, because if you think about the last, let's say, 25 years, the uncertainty estimates in the sort of bounds in contrail warming haven't changed a whole lot in 25 years. And it's kind of obvious why. When you think about the dynamics of scientific research, there's a whole load of estimates, some tens of papers, they have their different estimates, and we have uncertainty bounds based on all those studies. Now, the next marginal study that comes out, and it could be a great study, it might say, well, warming is double what we thought it was, or it might say warming is half what we thought it was. In either case, that would be within the existing uncertainty distribution, and so it's not going to change the distribution. The alternative is that another study comes out that's 100 times higher or 100 times lower, but that study will not exactly be ignored, but it'll be set aside until many other studies confirm that. So in a sense, we have this uncertainty range, and it's not going to change anytime soon. It'll take a long time, probably decades, for it to gradually shift over time. So basically, if somebody comes along and says, well, the science is too uncertain, we have to wait longer, what they're essentially saying is we have to wait, decades, 20, 30 years for that to really change. And I think given that we have those decades of research in the area that says that, well, maybe it's as warming as CO2, maybe it's twice as warming, maybe it's half, maybe it's a third, no matter what the answer is there, it's still important and we should do something about it. And we have to do that just understanding there's this uncertainty. But I think, so I think that sort of shift in understanding how you deal with uncertainty from, oh, we need to do more research, to, well, let's do more research, sure, but we need to take action in the context of that research. That'd be my number one thing. So that's sort of the prerequisite for the agreement to take action. Then I would say a second topic is that, so this is number 2 in the list of answers. The second thing I think is that while we sort of have had some very early preliminary trials in contrail avoidance, and we've simulated it ad nauseum going back decades, people have simulated contrail avoidance, we still don't actually have a verifiable practical way to do it in reality. So that's sort of, in a sense, that makes it sound like it's sort of not doable, but this is one of those problems where we'll throw some tens of millions of euros or dollars or pounds or whatever into it, and we'll solve it, right? It's not fundamentally that hard, but we do have to put those tens of millions of dollars, euros, or pounds into it and do the research and do the technical demonstrations and verify it. And many people are working on that. So my group at MIT, there's teams in the EU and the UK and other places that are really working on this. And we're making tremendous progress. But it's not like literally today we could do it and say it's successful. I mean, you could do it and say you did it, but verifying it really worked, using satellite measurements to prove it really worked, and all those sorts of things, that's not quite there yet. So there is a need for sort of some level of patience in the order of a few years and some tens of millions of euros or dollars of investment to make that technology happen and demonstrate it. So this is not kind of quite turnkey, but it's a pretty quick win. Then the third issue I would say is that in this conversation that's beginning to happen in the EU in particular, is how you sort of regulate it, or maybe not regulate it, but create the market structure, the incentive structure, or whatever structure it is to make contrail avoidance happen in practice. And I think it's important to start that discussion now, because it's probably about as hard as the technical discussion in terms of figuring out how to do it. And I think it's also a discussion where we're really not there yet, and you have seen some evidence of people kind of running ahead of themselves, leaping to solutions, and I don't think we really have a clear idea of what the best approach is to deal with that yet.
Thanks for that, Stephen. Yeah, nice summary on the 3 key barriers to large-scale implementation of.
Say what they were again, because I've forgotten them now.
Yeah, well, the first one was about uncertainties. And in light of the recent David Lee paper that came out last November, touching on these non-CO2 uncertainties, a lot of the basis of this paper was saying that we probably shouldn't be pushing ahead with contrail avoidance straight away. We should definitely be focusing more on CO2 for now, and holding back and making sure that we reduce these uncertainties to an acceptable threshold. Where do you stand on this side of the debate as to whether we should go ahead with it within maybe the next 5 years, or should we hold off and really just way to improve the science?
Well, I work very closely with David Lee, and he's a fantastic scientist who I have a huge amount of respect for, and we discuss this particular issue quite often. And I think the area where we have slightly different perspectives, and this is not really a scientific judgment, this is in a sense a philosophical or political judgment, is that he would take the view, and I'm sure he'll write to me if I mischaracterized it, that you shouldn't trade off any CO2 for contrails because CO2 is more certain and very long term. And I think that's quite a reasonable point of view to say, to have. I would take the view, which is a sort of doesn't change in the science, but it changes in the interpretation, which is that, well, we have this evidence base for contrail warming. The warming is very significant. It's comparable to CO2. And we know we think we could eliminate it for something like an extra 1% CO2. Now, the reason for that is that we would change the flying patterns of the aircraft very slightly, and we can get into that later, in a way that probably would cause something like 1% more fuel burn. And so sort of to first order, you'd be eliminating most of the contrails in exchange for something like 1% more fuel burn. Now, I think many people will say, well, eliminating half the warming in exchange for 1% more warming in the CO2 component, that sounds like a good deal. On the other hand, if you focus more on the uncertainties, you say, well, let's wait until we're sure. And both of those are very reasonable perspectives. My view, I think, is that the way to sort of square this circle is to say, well, let's move forward with contrail avoidance research and technical demonstrations, and move forward on the policy discussion. But frame it in the context of, well, we'll move towards doing contrail avoidance, rigorously and carefully with satellite verifications. But we'll take the long-term view that if we get to the point where we do contrail avoidance, let's say in, I'm not sure how many years, but it's hopefully faster than 10 years. Maybe it's even 5 years. But if we get to that point, we should be doing it in the world of no increase in CO2. And there's many ways you could do that. One would be to, for example, invest more in more efficient flight patterns, so air traffic control or optimizing the flight. You could say, well, you'll do that anyway. Another way could be to say, well, we'll guarantee to offset the extra CO2 with using more sustainable aviation fuel that decreases the net CO2. So I think essentially, environmentally, everything has to get better. And the right answer for warming is zero. So this just affects the vector of how we get there. But I would advocate moving forward with ambition and rigor in contrail avoidance, but doing so in a way that doesn't increase CO2.
Ambition is definitely a good keyword for us. Basically, you mentioned that it is possible to avoid those contrails maybe in the perspective without significant fuel penalty. There are two major approaches to this. One would be to alter the flight plan before takeoff, and the other one is to make deviations with very up-to-date data right in the cockpit during flight. Could you maybe explain to our listeners how exactly does this work, this so-called tactical avoidance, so the latter case?
Yeah, I mean, maybe just an overview of both. So in the ideal world, you would, download a weather forecast, and you can just go to online and just download that and download a contrail model, and you can just go and do that. And then, in a matter of days, you could put together something that would tell you quite how to fly your plane. And if life was that simple, it would be fantastic. Unfortunately, most of us have experienced that weather forecasts are not perfect. And in particular, weather forecasts, 6 or 8 or 9 hours ahead when you're doing the flight dispatch compared to the end of the flight, are definitely not perfect. And they don't need to be perfect to be useful. But realistically, what the forecast that far out will tell you is the likelihood of contrail formation. It's a bit like when you look at your phone in the morning to decide, do you take an umbrella to work, and it'll say 30% chance of rain at 1 p.m. So you might take an umbrella in case it rains when you go for lunch. But when it comes to 1 p.m., you won't leave your umbrella in the office mindlessly because the 30% rounds to zero. You'll look out the window and see if the rain cloud is over you at that moment in time, and if it is, you'll take the umbrella, and if it isn't, you won't. So it's going to be similar with contrail avoidance, where we need the forecast to tell us what's the propensity of regions that are cold enough and humid enough for these ice clouds to form, these contrails to form. And that will inform us as to should we put in some more fuel, essentially. Should we add in 2% more fuel, for example? But then when we're actually flying, it could be 6 or more hours later when we're in a particular region that might form contrails. We're not going to rely on that forecast. We'll use the best up-to-date forecasts combined even with observations from satellites as to where contrails are forming. And that way we can really refine where it is. So in a sense, it's just sort of the analogy of how we behave anyway when it comes to rain and clouds, right? We don't know precisely where the cloud will be in 6 hours, but we can just see it at that moment in time and make a decision accordingly.
I'm smiling. You can't see it on the podcast because you just answered like the 2 follow-up questions to that as well, like almost literally. Very interesting to hear that, especially. One point I want to drill down is this additional fuel requirement that enables you to do deviations, especially the vertical deviations during flight. So is this something where we have maybe quantifications on, like it's a trade-off, right? More weight means more fuel burn, just to have the potential to do that during flight. So can we quantify this trade-off at this point?
Yeah, I mean, I would say yes, but with a caveat. So the yes is that we've done simulations, and the caveat is we've done simulations, right? So there needs to be real world experiments with commercial aircraft, civil aircraft, such as MIT are partnering with Delta in doing, and there are others around the world. So for example, we've estimated that 80% of contrail avoidance missions would need less than 5% more fuel burn to avoid all contrails. And I think what that implies is that there might be some percentage of cases where you could avoid contrails that you might just not do it because, for example, you couldn't add more fuel, right? The aircraft is already maxed out in the fuel load. And if that happened to be one of those cases where the percentage extra fuel was let's say more than a couple of percent and the aircraft was already maxed out, then, well, you just couldn't do contrail avoidance in all the cases because you'd need to keep your reserve, which is the legal safety required minimum. But having said that, the vast majority of flights or aircraft fly at something like 60% of the design range. So there's a massive margin in most flights. So in the majority of cases, there's a huge margin. And in almost all cases, there's a margin of at least a couple of percent, which would cover most of the avoidance maneuvers. So the number of cases where you would be kind of fuel capacity limited would be extremely small. I don't think we have quite a perfect handle on what that is yet, but it's probably so small as to not being that relevant to considering, whether we proceed with this. It's really just, could you eliminate, 90% or 95% of the contrail warming? That's the question.
And you mentioned the live trials being done between MIT and Delta Airlines. Mm-hmm. Could you expand a bit on how exactly you carried out contrail avoidance with these trials, and maybe how those trials were different to American Airlines and Google?
Well, they're very similar, actually. So, for example, we worked with Google and developed a lot of the underlying approaches together. So, I'd say none of those trials yet are at the point where it's, we've said we have a result that is kind of scientifically conclusive and stands up to all the statistical analysis. All this stuff is all ongoing. I think the big, and both of them were based essentially on satellite observations and the same satellite and the same algorithms and everything else. The big difference is really between the 2 American trials that have been going on that are very observationally based, and the one in the upper Maastricht airspace, which was based on using forecast regions and then having air traffic control reroute the aircraft around the forecast contrail forming regions. I think in the long term, you will end up needing a hybrid of both of these in that it's kind of hard to imagine not having air traffic control involved in large scale avoidance. And it's also hard to imagine doing this successfully and verifiably without having satellite observations, because then you essentially can't really verify it and it's probably going to be less effective. So in the long run, all the stuff will kind of fuse together, but the starting points happen to have been different.
I think Dr. Adam Durant from Satavia made the point that if we were to go ahead and eliminate all contrails from airspace, then we'd be in a situation where detecting contrails using AI and satellites, that would almost be rendered obsolete in a sense. So what he says is that we need a combination, exactly as you were saying, between these 2 approaches to really make sure that one of them doesn't outweigh the other in some sense.
Yeah, I'm not sure it's really a case of one outweighing the other. I think it's more that to have good forecasts, you have to have observations. and the observations have to be ingested or assimilated into the forecast to nudge it, as they say, to correct it as it goes along. Otherwise, the weather and climate is a chaotic system. So even if you had nearly perfect starting conditions, the simulation will diverge from reality no matter what. So you're always going to have observations. So there's no scenario where you could have a perfect forecast, for all time. It will always be nudged by observations. So I think it's hard to foresee a case where we wouldn't need both, essentially, in that you'd want to have a forecast as good as you can, but you'd always want to be able to improve it with observations.
Do you think there's any scope to use some of the recent AI weather modeling approaches, such as Google GraphCast? So maybe integrating those into contrail prediction models? I'm sure, yeah. And we've done quite a lot of work on that at MIT as well, and you can definitely improve, the forecast over either one alone, either the pure observationally based or pure forecast based. So in a sense, the machine learning tool set that's available now is so well developed that you can quite quickly do things like that, make improvements. And I think over time there'll be a lot of refinement of that. The challenge always is with machine learning approaches is that is obviously verifying it and application outside of its range of applicability. So it's still a case where those tools will be extremely helpful and will refine how effective we are, but you'll still want the verification observation to be sure that what you're doing is true, especially given we're in a world where the climate is changing. So even if it works now, if as the climate changes, what works in the past is going to shift in its effectiveness over time, just obviously given this climate change. So lots of retraining of models, I'm guessing, based on the updating climate. Continuous improvement, and I think it'll be an area of huge progress in the years ahead. So at MIT, are you using these models to predict contrails in terms of the microphysics, or is it more the large-scale effects that you're modeling? Is it the subgrid processes or the grid scale processes? Yeah, we so far we've taken quite different approaches in those two scales. So at the kind of small scale, we have microphysical models that model the ice distribution and things like that, and how the ice particles settle and evaporate and so on. Then at a large scale, it's been much more focused on using machine learning to process real-time satellite imagery to extract where the contrails are. It could be possible to kind of use machine learning at the very small scale, but it's not obvious that there's as big a win to be had there, because all you'll be doing is emulating a model that we can run anywhere, essentially. So in a sense, it's sort of not, we might do that, but it'd be more if there was a reason, for example, we wanted a rapid emulator of a model or something like that.
But since time is so important for this, I mean, we can bring down the computing resources needed, right, to make a prediction. And even if we emulate the microphysics schema that is used within a bigger model, it might bring down the resources needed, so we could increase the frequency potentially of running these predictions. So this is basically time versus accuracy, right? And if we can increase the frequency, so it's more short notice, wouldn't that bring a benefit?
I think that's true, and I think if we're at the situation where simulating individual contrails in great detail really makes sense operationally, then that would be one way to create a sort of reduced order or surrogate model, would be to train it using the machine learning toolset. There are also many other tool sets that have been developed over decades. The surrogate modeling, reduced order modeling is it's a big field, and there's many approaches you could take that have different pros and cons. And the machine learning tool set is one approach, and you can sort of mathematically prove in a sense that a deep neural net is essentially a curve fit that could basically fit anything. So it can be very effective at kind of reproducing complex models, but it doesn't mean it's always the best way to do that. But I think the other aspect of this, I'd say, is that it's not clear that simulating individual contrails in massive detail really makes sense right now. It does from the perspective of saying, well, we can simulate the scenarios and say how much benefit we can get in terms of reducing contrail warming, or kind of have some statistics on how much warming will be reduced, and how many contrails might be warming versus cooling, which could happen. But for any individual contrail in the real world, the simulation of the contrail is so dependent on how humid the air is, what's called supersaturation, and we have such massive uncertainties in that supersaturation that kind of a detailed simulation doesn't really make that much sense in the context of those huge uncertainties. So probably it'll be some time until it's kind of is really that meaningful to tie in these very detailed simulations, just because we have such a rough understanding of humidity in the atmosphere right now.
Okay, let's assume for a second that we have IAGOS, right? So we have some kind of in situ data, including humidity sensors, that provide us with a ground truth, let's say, to test our models against. Let's assume for a second that maybe more aircraft were equipped with sensors.
All aircraft.
Yeah, all that.
And then everything I said is wrong, right? I mean, I think that would be the ideal, right? Is to have all aircraft having humidity sensors, and then you could in real time simulate pretty accurately what the contrail warming would be, and you'd have an incredibly dense network to constantly update weather models and everything else. So I think in that world, things have changed, and that world could come to pass because you have investments being made in multiple countries in developing cheap, low-cost sensors that could do this, like in the US, ARPA-E, which is the Advanced Research Project Agency for Energy, is now investing in this exact topic. And ARIA in the UK, which is the sort of a newer agency in the UK, is considering that. I'm not sure how if they're going to go ahead with that, but this really could happen. And so for that reason, it really does make sense to continue advancing the small scale models, because as well as kind of scientific interest, they really could have real world application in the years ahead. And you obviously have to do these things in parallel, otherwise you'd be waiting around for years once one thing's ready.
Is there anything in ARPA-E that you're particularly curious about? Any topic that was mentioned or direction they are going that maybe could be a disruption?
Well, I mean, this might sound, it probably is a bit absurd, it doesn't just sound absurd, but I often like to think about long-term research as how would it be in Star Trek or something like that. And in my mind, the kind of having a probe kind of sticking out the side of an aircraft to measure humidity with all the vagaries, and that's fine, right? But I mean, how would it be in Star Trek as having some beam that shoots ahead that kind of detects what the humidity will be in the distance ahead and avoids contrail forming regions before you get there? So if that turns out to be possible, then I think that would be great. And it's maybe LiDAR viewing small ice crystals or something like that could be a way to do that. So it's not necessarily physically impossible, but actually developing the real world technology and demonstrating it in a package that could go on an aircraft, that's some undertaking that will cost some millions of dollars or euros to do.
So this is all related to the topic of predicting ISSRs. Of course, having onboard sensors is potentially a very good way to improve the accuracy of predictions. What other areas do you see advancing forward that we can really put some time and money into to improve these ISSR predictions?
I think the measurements is the big one, both in situ and space-based, so satellite-based measurements. I think once those become more widely available, it would just be a case of the organizations that are the kind of keepers of the world's best weather models, like the ECMWF and NOAA and others, prioritizing in their engineering roadmaps getting more accurate high altitude humidity, which so far sort of hasn't really been a priority because it doesn't really matter for the existing applications. So it's I don't think there'll need to be a magic wand to make massive progress there. It'll just need to be a priority for those organizations to develop their weather models with that as an objective.
I'd like to ask a question about a topic that is recently discussed more, and that is the big hitters. So flights that cause the majority of the warming caused by contrails. And I want to challenge this maybe a little bit, because I understand that from a scientific point of view, there are such flights which, create massive contrails that persist for a long time with a great effective radiated forcing. But in order to then implement this or put this into maybe even regulation, I find it very tricky, because it's like at the other end of the spectrum where you need to nail everything. You need to basically understand perfectly what each flight causes in terms of the contrail warming. So is this a helpful debate to look into the big hitters?
I think it's a helpful debate to help us collectively arrive at a sensible policy outcome, which I don't think we're quite there yet. So in a sense, the kind of rational but naive approach would be to say, well, we should measure the warming of every flight precisely, and then kind of charge people according to how much warming that flight caused, right? But then, just think about it from a sort of even a family perspective. Let's say, you're a family living in London, paying huge rents and struggling for money, and you've saved up to go on holiday to Spain, and you paid your €100 a person for the ticket, £100 if you're going from London to go to Spain. And then you suddenly find out that the warming from your flight was 20 times higher than the average, which could easily be the case just because of bad luck. And suddenly you get a bill for a couple hundred more pounds, right, for the warming. I mean, clearly that's not a fair or rational thing to do, to kind of charge individual consumers and families for things they have no control over, given you don't know what the weather will be like at the point you're booking, right? So clearly there has to be some aggregation there, maybe at the airline level or at the route level or whatever it is. The second piece of that is that you can't even, we can sort of run models and say, well, there are the big hitters and there are the less control-forming flights. And we can come up with numbers and, print out an Excel spreadsheet or whatever of ranking them. What that really tells us is that there is variability in the real world, but because real world weather is quite uncertain and we don't really have the measurements at high altitude to know what really happened, the correlation between that exact rank ordering and reality is probably pretty limited, right? It will tell us the kind of statistics of how these things vary, and the averages will be quite good, but the actual specific rank order, may or may not have much validity to it, and we just don't know at this point. So that again tells us that we have the knowledge to do things that apply on average and to have policies that apply on average, but charging things sort of at a very detailed level isn't supported either by the science, and if it was, you'd still want to do that in a way that doesn't penalize kind of individual people for making decisions that then they get charged for, where they had, be like penalizing somebody for not forecasting the weather, right? That doesn't make sense. So I think we have to think really carefully about the policy frameworks that deal with the scientific uncertainties as well as individual equity in a sensible way.
So integrating non-CO2 effects into Google Flights, say, as an example, you think that this is potentially, is still quite a few years off, right?
I think there's ways to do it that are useful. So, for example, if you say on average flights cause twice as much warming as the CO2 and give the CO2 number, there's a lot of scientific basis for that. You might start trying to advance beyond that and go by kind of time of day or region or something like that. But it wouldn't make sense to go to sort of the precise flights on a Tuesday morning at 9 a.m. because the science really isn't there yet. And that's not even necessarily helpful as a policy solution anyway.
It's all about certainties here. And one question that I need to ask you as we are wrapping up this episode, we are going to finish on a positive note, but I'd like to have your take on a critical question, and that is, I heard some experts say, well, there is this concept of a false positive, meaning that you predict an ISSR to be there, and it's actually not there, but then you divert the flight and you actually divert it into an ISSR. So this like double negative effect. Is there a way we can quantify the chances of this to happen? Is it a valid argument?
It's definitely a valid argument. I mean, that can happen and does happen in the sort of PreTrails that happened. I think the way to tackle that is just with, as well as the ambition to move quickly, the rigor to evaluate it robustly. And that means either satellite measurements or some other real measurements to see what's really happening. And you won't have a 0% false positive rate, but you want to figure out what is an acceptable rate there. And in some sense, there'll be a trade-off between false positives and avoiding contrail. So you'll figure out what the optimum is, considering all the factors. But that's a very, very doable problem. And in some ways, a lot of this stuff has analogs in other areas like air pollution. So if you think about NOx emitted from cars, right, we heavily regulate NOx emissions from cars so that they've come down in the case of diesel vehicles by some 95, 99%. But if you think about what NOx actually does, well, historically a big concern was ozone, and NOx emissions sometimes increase ozone and sometimes decrease ozone. But we didn't try and sort of ask drivers to turn up the emissions control system or down on account of an individual route they might be driving. We instead say, well, on average, we know that regulating NOx emissions of cars is great for public health. And it could be the case that some percentage of those times when the emissions control system's in use, we're causing a bit more CO2, which does happen in reality for cars too, in order to eliminate the NOx emissions. But we're certain that on average, that makes sense for society. And similarly here, over time, we'll figure out that there's a trade-off where we have high confidence that this trade-off makes sense on average, and it won't be perfect in every precise case. But just like with environmental controls in air pollution, we're pretty confident it's a net plus for society.
You managed to turn it around into a positive aspect. I like that. And that's a good note to finish on. As we have this tradition, our next guest is Dr. Alejandro Bloch from IATA. And I met him in Madrid last year as he was moderating the panel discussion with Florian Allroggen from MIT as well. It was very interesting. And so this is your chance to direct a question to IATA, to Alejandro.
Well, Alejandro is a great contributor to this whole debate as well. And I'll give him a hard question then. So it's, does he see prospects for a global solution to contrails and contrail avoidance and or coordinated regional approaches?
It's a yes/no question, so I really hope it's going to be a yes.
Well, I was hoping he'd expand on. I was hoping he'd expand on the yes or no, but I guess we'll see what he says.
We'll try our best. Well, Stephen, this has been an absolute pleasure. We've been looking forward to this episode for quite a while, and we'll stay tuned with everything that you do. You mentioned the tremendous progress that has been going on so far, and we're definitely looking forward for the year of 2024. Thank you.
Likewise, and thanks for having me. Thank you.
Great. Thanks, Stephen.